Hello guys, hi future doctors. I am Dr. Shivangi Shukla and today we will be discussing about a very important topic, that is myoglobin and hemoglobin. Now this myoglobin and hemoglobin we'll be taking up uh, a lot. We'll be borrowing a lot of content from our last session that was on amino acids and the structure of proteins. Now if you're not thorough with that, please go back to that session. If you haven't watched that session, go back to that session and revise the structure of proteins, because we need to be extremely adept at the structure of proteins, all the structures, that is alpha helices, beta sheets, and the primary and the higher orders of structure of proteins, the nature and the characteristics of amino acids and the different types of amino acids. All of that has to be extremely clear to us. It should be on our fingertips before we move on to the rest of the chapters, especially for myoglobin and hemoglobin. Now, myoglobin and hemoglobin, as the name suggests, myo is related to muscle, right? Myo is related to muscle, and heme or hemo is related to redness, right? Globin, as we have already read in the earlier session, globin is a type of protein, that is a globular protein, right? Because we read we read about globular proteins in the earlier session also, how globular proteins are formed. Remember beta barrel, a type of a type of protein structure present in globular proteins. If you haven't, please go back to that session, because again and again I'm telling you, we'll be borrowing a lot of knowledge from that session for this session. Okay, so let us begin. The first slide here, I have purposely kept blank. Why? Because after this session is over, we are going to come back to this slide and we are going to draw or tabulate the similarities and differences between myoglobin and hemoglobin, because in comparison there will be a few points of similarities and a few points of differences, obviously. So we are going to tabulate, and it is an extremely important topic for your short notes as well. Okay, so it is very important from your exam point of view, for your understanding point of view, and to clear your concepts as well. Okay, so definitely we're going to come back here and you're going to tabulate it as we speak. So keep on jotting each and every point that you come across in your memory, so that you come back and reciprocate it here. Okay, so heme. Now, heme is central to discussion here. Why? Because it forms this basis of structure of both myoglobin as well as hemoglobin. Now, what is heme? Heme is an iron containing cyclic tetrapyrrole. Now, this seems to be very difficult or very fun to remember. So let us break it down as we do. We break down complex things and then we understand simplified concepts. Tetrapyrrole. There is something called pyrrole. Tetrapyrrole means four pyrroles. So four pyrrole molecules arranged in a cyclic fashion containing an iron or a ferrous atom also. Okay, so this is what is heme. Heme is a cyclic tetrapyrrole, that is four pyrroles arranged in a cyclic fashion with a central iron. Okay, now we'll also draw the structure of heme as we discuss. So pyrrole, how do you draw pyrrole? We are going to draw four molecules of pyrrole like this. Okay, now it will contain a double ring also, but a double bond also, but we are not going to draw a double bond right now. I'll make it easy for you. I'll simplify how to draw double bonds. Okay, so okay, understood. So this is one pyrrole, second, third, and fourth tetrapyrrole arranged in a cyclic fashion. Easy. Now they are linked by methine bridges. What is methine? Methine is one carbon with one double bond and two single bonds. Okay, so a carbon containing one double bond and two single bonds is what constitutes methane bridges. Okay, it is used to connect cyclic compounds. Like here, it is connecting the cyclic tetrapyrrole rings. Otherwise, what will happen is they're going to disperse. So it needs to be connected, right? So this tetrapyrrole, I'm going to draw the methane bridges, I'm going to draw in another color. So you connect it like this. The alpha carbon is going to be connected. So this is the alpha carbon, this is the beta carbon, okay? So this is how it is connected. So this is the um, methane bridge, okay? Now we'll start drawing the double bonds, okay? So every alternate carbon, every carbon will have a double bond here, but not more than one, okay? So suppose we'll start with here. This carbon has one double bond, okay? Now it is not going to have a double bond with this because it already has a double bond here. So this carbon will have a double bond like this. Got it? Now, so this carbon has a double bond like this. Now this carbon already has a double bond here. This carbon cannot have a double bond here. So the next double bond will be here on the methane bridge. So this methane carbon already has a double bond. Now this one will be single because a methane carbon only has one double bond. So now this carbon is going to have a double bond like this. Now this carbon cannot have a double bond again here with this. So this carbon will have a double bond like this. Okay, now this carbon cannot have a double bond again with this. So what will happen is this will have a double bond with this. Understood? Now this methyl double bond is already over. So now this carbon is going to have a double bond like this. Okay. Now this carbon cannot have a double bond here, so it is going to have a double bond like this. This already has a double bond. The methane carbon will have a double bond here. Now this carbon already has a double bond, so it is going to have a double bond here. Got it? And then the methane carbon will have a double bond like this. So this is how you draw double bonds. Or each carbon will have a double bond, but it cannot have a double bond with adjacent carbons, with both the adjacent carbons. So it is going to have a double bond with alternate carbons. Understood? So this is how you draw the double bonds in this cyclic tetrapyrrole. Now you insert a central ferrous atom. Ferrous. Remember, if the atom is oxidized to ferric, then the structure will break. Now this ferrous atom has 6 coordination states, or it has 6 coordination bonds. 4 bonds will form between the pyrroles. One bond will be formed with oxygen during the formation of oxyhemoglobin, and one bond is formed with a different special molecule that we are going to read on later on. Okay. Now, one more thing, and the structure of heme will be completed. The next is the substituents at the beta positions. Remember, this is the alpha carbon and this is the beta carbon. So there will be substituents at beta positions of each pyrrole ring, of each cyclic pyrrole as well. Now, how are these substituents arranged? They can be methyl, vinyl, or propionyl substituents, and they are arranged as M, V, M, V, M, P, P, M. So M is methyl, V is vinyl, P is propyl. Okay, so we'll just quickly draw it from here. M, V, M, V, M, P, P, M. So this completes the structure of heme. Understood? You draw 4 pyrrole rings, you connect them with methane bridges, then you start drawing the double bonds alternately. Okay, alternately you draw double bonds. You should ensure that each carbon has only one double bond. Okay, so that is all that you have to ensure. Then you draw a central ferrous atom. You link all the pyrrole rings with coordination bonds. Then you draw MV, MV, MPP, M, the substituents at the beta positions of the pyrrole ring. Understood? So this is the structure of heme. Now, very important thing is, all the pyrroles and the methine bridges, they are present in a coplanar fashion. They are present in one plane, and the ferrous atom is present in a slightly different plane, though not too much, a slightly different plane of a few nanometers above the plane. Okay, a very very slight difference, but it is significant enough to be considered here, because it is what forms the basis of the physiology of hemoglobin and myoglobin, especially the oxygen transport. Okay, so, and because there is metal inside this protein, there is a presence of metal, that is ferrous. Metal is present in the protein, therefore it is a metalloprotein. So, hemoglobin, myoglobin are examples of metalloprotein. Other examples of metalloproteins are cytochromes containing copper and iron, and chlorophyll, which has magnesium. Okay, so these are other examples of metalloproteins. I hope this structure is clear to you. So we studied about heme, that forms the part of the structure of both myoglobin and hemoglobin. Now we are going to read about globin. What is globin? Globin is the protein part of these molecules. For myoglobin, myoglobin contains 8 right-handed alpha helices. Okay, 75% of myoglobin is composed of right-handed alpha helices. Alpha helices, we read from the last, borrowing from the last session, alpha helices are, all the stable alpha helices are right handed. Why? Because the left hand, because all the amino acids exist in an L form. All the alpha amino acids exist in an L form. Now what is L form? L form is where the R chains or the side chains of the amino acids are present on the left hand side in the Fisher projection. So if you twist this in a left-handed fashion, then all the R chains are going to crowd. If they're going to crowd, then they're going to repel each other, and the alpha helix will be unstable. Therefore, for an L form of alpha amino acid, you need to have right-handed alpha helices for stability. Therefore, myoglobin contains right-handed alpha helices. There are 8 in number, and each alpha helix will be formed of amino acids, because alpha helix is a polypeptide chain arranged in a twisted fashion. So each polypeptide chain in the alpha helix will contain a few amino acid residues. How many residues? Either 7 or between 7 to 20 residues. Okay, so these residues are numbered from 1 to 20, and these alpha helices are numbered from A to H. Okay, so suppose the first alpha helix that you are, suppose you want to talk about the 7th residue on the first alpha helix. So you will name it as A7. Got it? So this is how you remember it. Okay. Now, like any globular protein, the surface of the globular protein is charged and polar, and the interior is non-polar or uncharged. Okay. Similarly, in myoglobin also, which is a globular protein, you have the surface of myoglobin is polar and contains charged side chains of amino acids, and the interior is non-polar or hydrophobic. Okay. Exceptions to this are the 2 amino acids about which we are going to read. Now, histidine F8 and E7. These are the 2 exceptions, and we are going to read about their unique role in hemoglobin and myoglobin biochemistry and physiology. Now, the heme molecule lies in a crevice inside the globin. Now, this is the globular protein. Okay, globin. This is a crevice inside which heme will lie. Okay, heme will lie here. Okay, now this is the E and the F helix of globin. This is globin. Okay. This is helix E and this is helix F. The heme molecule will lie in the crevice between E and F. Okay, now this crevice, this here is non-polar and this surface is polar. So the polar groups of heme, the polar propionyl groups of heme, remember we read MV, MV, PP, M. So the PP, propionyl groups of M, will be facing the surface of globin, and the rest of the heme will have hydrophobic interactions with the core of globin, okay, through non-polar interactions with the core of globin. Okay, now remember we studied about the 4 coordination positions of iron. The 5th coordination position of iron is occupied by nitrogen from imidazole group of F8 proximal histidine. The 6th will be occupied by oxygen. So we know how all the 6 coordination positions of iron are occupied. Now you have to know, you have to focus on the word proximal and distal as well. Now F8 histidine is proximal, that is it is near to heme, and E7 is distal. Now how do you remember this? Distal is from D. E and D are adjacent in the alphabet. So E is distal and F is proximal. Proximal means it is near to heme and E7 is distal to heme. This also you should remember, it is of importance. Why? We will now draw it here. So now let us draw. This is the plane of heme. We know that the tetrapyrrole and the tetrapyrrole and the methine bridges are coplanar. This is iron, okay, ferrous, okay. Now this ferrous forms a coordinate bond with this F8, the proximal F8. And a distal E7 is present on the opposite side. Remember, on the opposite side of the ring, there will be a distal E7 present. It is not forming a bond, it is just staying here. Okay. Now, what happens is, this iron has to attach to oxygen. Now, when oxygen forms a coordinate bond with iron, what happens is the O can be easily, the bond between here, the bond between oxygen and iron can easily be accommodated in this space here. Okay. Whereas when carbon monoxide will come and form a bond here, when carbon monoxide will come and form a bond here, then there will be no space to form a bond between, and there will be a lot of hindrance from this histidine E7. Okay, it will cause a lot of hindrance, that is steric hindrance, that is it is not going to give space for this carbon monoxide molecule to come and form a bond with ferrous atom here. Okay, now why is it so? Why did I draw the oxygen in a slightly tilted manner, and why did I draw carbon monoxide here in a vertical fashion? This you're going to read next. Okay. So what happens is, the carbon monoxide molecule, the free electrons contained here are linear. The lone pair of electrons that are present in carbon monoxide are linear to this double bond. Whereas in oxygen, the lone pair of electrons that are present on each atom form a 120-degree angle with the double bond. So this is how an oxygen molecule is. The lone pair of electrons are forming almost a 120-degree angle with this double bond, whereas the lone pair of electrons on the carbon monoxide atom are linear to each other, are linear to the double bond. So coming back here, if this carbon monoxide is going to form a coordinate bond with ferrous atom, then it is going to donate its lone pair of electrons. For that to occur, the lone pair of electrons has to come near the ferric atom, and therefore carbon monoxide has to adjust in a vertical fashion. For that, you don't have space here because his E7 is nearby. It is providing steric hindrance, or it is providing crowding. It is not letting it come. No, you cannot adjust here. Whereas for oxygen, if oxygen stays like this, the lone pair of electrons is present in a 120-degree angle. So it can easily adjust in a horizontal fashion like this. Understood? So oxygen has the space to come and form bond here, because it cannot be sterically hindered by E7. But carbon monoxide and its arrangement of lone pair of electrons is such that it has to be vertically adjusted, and his E7 is not allowing it any space. So there will be steric hindrance from histidine E7, and because of the arrangement of lone pair of electrons in a linear fashion in carbon monoxide as compared to 180-degree in oxygen, this carbon monoxide cannot easily adjust in the heme iron. Therefore, at normal concentrations of carbon monoxide, the carboxy hemoglobin, that is containing carbon monoxide, hemoglobin combining with carbon monoxide, is not stable. Okay, but oxyhemoglobin is stable. Therefore, you may be wondering, we have carbon monoxide around us. It is a product of catabolism of RBCs. It is also a product of incomplete combustion of fossil fuels, always there in the environment. So why is carboxyhemoglobin not getting formed in spite of CO, carbon monoxide, being 25,000 times having more affinity for hemoglobin? The heme group has 25,000 times more affinity for carbon monoxide compared to oxygen. Still, routinely, carboxyhemoglobin is not getting formed. Carboxyhemoglobin is only getting formed at very high concentrations of carbon monoxide. Why is it so? Because of the structure of hemoglobin, where there is steric hindrance from the distal histidine E7, and the carbon monoxide has the free pair of electrons, the lone pair of electrons in the carbon monoxide molecule is arranged in a linear fashion to the double bond. Okay, so this molecule cannot adjust or cannot form coordination bonds with the iron ferrous atom, whereas the ferrous atom can easily form coordination bonds with the oxygen. Why? Because the lone pair of electrons on oxygen is there at an angle of 120-degree with the double bond. Easy. So there is no steric hindrance for oxygen. But when there is a high concentration of carbon monoxide, then what happens is the affinity prevails and carboxyhemoglobin is formed. Okay. Now when this we remember how we discussed that iron is slightly outside the plane of heme. How much outside? 0.03 nanometers. And where it is towards the F8 ring, that is, it is slightly below, about 0.0 0.03 nanometers towards the F8 ring. Why is it so? Because the iron does not have any bonds here. Okay, see, ferric iron has bonds here, and with it has bonds in this plane, it has bonds below this plane, but it has no bonds above this plane. Therefore, all the four bonds in this plane are going to get cancelled, and it is going to get pulled slightly below because of this coordinate bond, and therefore it is slightly below the plane in a deoxygenated state, about 0.03 nanometers below. Now, when oxygen comes and attaches itself to the ferrous form of iron, then what happens is there will be a slight pull above. So the ferrous form will rise, it will move, the ferrous iron will move up. Okay, and it will move within 0.01 nanometers within the plane. So 0.02 nanometers above, it is moving by 0.02 nanometers, and now it is within 0.01 nanometers of the plane of heme. It is very insignificant, but it is significant when you consider the physiology of hemoglobin. Okay, because this oxygenation will move this iron. When the oxygen will come and attach itself to the ferrous form, the oxygen moves iron, and the iron will in turn move histidine F8, and histidine F8 will have other amino acid residues below in the chain. So those amino acid residues are also going to get moved up. So this small act of oxygen getting attached to the ferrous form is going to pull up iron by 0.02 nanometers into the plane of the of porphyrin, and which is going to pull histidine F8 also. It is going to pull the other residues attached to it also. That is going to trigger a conformational change that we are going to read later on. Okay, so this, you know, that there is motion of iron during oxygenation. Very important. The iron or the ferrous form moves in heme, and it pulls the histidine residues along, and the residues linked to it along during oxygenation. So this we know how there is a hindered environment or a sterically hindered environment for carbon monoxide in a normal state. Carbon monoxide is sterically hindered in a normal state from attaching to hemoglobin, and normally only oxygen attaches to hemoglobin. But at very high concentrations of carbon monoxide will get attached, because the affinity for carbon monoxide, that is 25,000 times stronger compared to that for oxygen, will prevail. Okay, I hope this lone pair of electron concept and the steric hindrance concept is clear to all of you. So this is what we have discussed about myoglobin. Now we are coming to hemoglobin. What is the difference between the hemoglobin molecule and the myoglobin molecule? Myoglobin, we read, was monomeric. That is, it just had one molecule of globin. Hemoglobin is tetrameric. It has two pairs. Two pairs means four. Tetra means four. You remember how in the last session we studied about the quaternary structure, monomers, dimers, tetramers. So the quaternary structure of hemoglobin is tetrameric. Got it? So two pairs of similar but distinct polypeptide units are present. Okay, two pairs. Now, depending upon the hemoglobin, we'll have these polypeptide chains. In adult hemoglobin, we have the adult hemoglobin is denoted by HbA. Okay, adult hemoglobin, we have alpha 2 and beta 2. Two alpha chains and two beta chains in the adult hemoglobin that all of us, the normal adults, have. Fetal hemoglobin, which is present in the fetus from the third trimester till around the first 6 months of age, fetal hemoglobin will predominate, and it has 2 alpha and 2 gamma units. Okay, so 2 alpha and 2 gamma. This is fetal hemoglobin. Embryonic hemoglobin. What is embryonic hemoglobin? There are different forms of embryonic hemoglobin that predominate during the first 3 months of life, in the first trimester. So Gower 1 has zeta 2 and epsilon 2. Gower 2 has alpha 2 and epsilon 2. And Portland can either be zeta 2 and beta 2, or zeta 2 and gamma 2. So these are Gower 1, Gower 2, Portland, all these are embryonic hemoglobins that get degraded or during the after the first 3 months of life. Then comes HbA2, which is a minor form of adult hemoglobin. It is present in minute quantities. It has alpha 2 and delta 2. Okay, so how many chains you studied about? Alpha, beta, gamma, zeta, epsilon, and delta. Okay, so in different forms they are arranged, and so every hemoglobin that you studied is a tetramer. The quaternary structure of hemoglobin is a tetramer, that is two pairs of similar but distinct polypeptide units. There will be two pairs. Okay. Now, what is P50? P50 is that partial pressure of oxygen at which a given hemoglobin reaches half saturation. What is a given hemoglobin? We have studied about different types of hemoglobins here, right? So any given hemoglobin, whenever will have, all these hemoglobins will have different P50s because they will have different affinities for oxygen. Okay, so adult hemoglobin may have different affinity for oxygen compared to fetal hemoglobin, compared to embryonic hemoglobin, compared to the minor form of adult hemoglobin. Therefore, P50, or the partial pressure of oxygen at which this hemoglobin reaches half saturation, that is half of the all half of this hemoglobin molecule is saturated, that is called the P50 of that hemoglobin. Okay. Now, for all hemoglobins, be it hemoglobin F, hemoglobin A, hemoglobin A2, or embryonic hemoglobins, for all the types of hemoglobins, the P50 exceeds the PO2 of tissues. That is why at the hemoglobin, it will not, it will tightly bind to oxygen, but at the level of tissues, it is going to release the oxygen. Okay, it is going to be saturated with oxygen, but at the level of tissues, it is going to release oxygen. Okay. Now, for an example, if you have to understand about P50 in greater detail, with an example, I can tell you. For HbF, or the fetal hemoglobin, the P50 is 20 millimeters of mercury. And for HbA, or adult hemoglobin, the P50 is 26 millimeters of mercury. So the fetal hemoglobin has a lesser P50. That means at a lesser partial pressure of oxygen, it is going to be half saturated, whereas HbA is going to be half saturated at a higher partial pressure. That means HbF, or fetal hemoglobin, has a higher affinity for oxygen. Therefore, this property helps the fetal hemoglobin to extract oxygen from the placenta. Okay, because the affinity with which the HbA is holding on to oxygen in the placenta is lesser compared to the affinity with which the HbF is going to draw oxygen. Understood? Next, the beta subunits in hemoglobin and the myoglobin are almost similar. The heme location of heme and the helical regions in the alpha helices, the presence of amino acid chains with similar properties, that is, the hydrophilic groups will be arranged outside and the hydrophobic groups will be arranged in the interior. All these are the similarities between myoglobin and the beta subunits of hemoglobin. The differences between myoglobin and beta subunits of hemoglobin are the number and kind of amino acids in the primary structure. Okay, so then of course there has to be a difference in the primary structure, otherwise they will be totally similar proteins. So the primary structure is different, but the secondary structure, tertiary structure, the arrangement is similar. The alpha polypeptide is also quite similar, but instead of the 8 helices, it has only 7 helices. Remember, myoglobin had 8 helices. Similarly, beta has also 8 helices, but the alpha polypeptide has just 7 helices. Okay. Next, next we come to physiology of hemoglobin. So one molecule of hemoglobin can bind to 4 molecules of oxygen. How? Because hemoglobin is a tetramer. So one molecule of oxygen can bind to one molecule of heme. So per hemoglobin we have 4 heme molecules. So there will be 4 molecules of oxygen per hemoglobin. Okay. After the first oxygen binds, the affinity for the rest of the molecules of oxygen increases. Okay, first oxygen will bind and it will pave the way for easy binding of the rest of the oxygen molecules. This is known as cooperative binding. Okay, now this cooperative binding is essential to maximize the oxygen loaded at the lungs, because you get a fraction of a second, less than a fraction of a second, to load the oxygen on the hemoglobin, because the blood is circulating very fast. So within one heartbeat, you have to load the as much oxygen as you can on the lung capillary bed. So for that you need to have cooperative binding. After one molecule of oxygen binds, the rest of the molecules should rush in with ease, and it should be offloaded at the tissues. Maximum should be offloaded at the tissues. So this cooperative binding helps doing both. The first molecule of oxygen the first molecule of oxygen binds to deoxyhemoglobin and it pulls the iron towards the plane of the heme ring. We know this, right? The iron is slightly below, about 0.03 nanometers below, because of the pull from histidine F8. Now, as oxygen binds, it pulls it by 0.02 nanometers into the plane of heme. Now, the his F8 residues which are attached to iron are also pulled, and the his F8 residues also pull the rest of the residues along. Now, these residues are attached to the nearby residues by salt bridges. Okay, salt bridges are ionic bridges. So, the carboxy terminals of these residues are attached to the nearby residues by salt bridges. Now, if they are pulled up, then these salt bridges will break. Okay, now once these salt bridges break, what will happen is the hemoglobin molecule will be slightly unstable and it can twist. Earlier, it had salt bridges to stabilize it. Now, the salt bridges are breaking. When the salt bridges have broken, what will happen is one pair of alpha beta subunits is going to rotate about its axis, and it is going to trigger a change in the structure of hemoglobin. Now, this is alpha. This is alpha. And this is the beta subunit. This is the beta subunit. Got it? Now, as the salt bridges are broken, suppose this alpha beta subunit, this one, is going to twist. This will twist about its axis like this. And then, like, suppose a wound up thread, you twist it like that. So the whole of the thread will have a conformational change. Okay, so suppose something is twisted, a thread is twisted, and then you twist it, or you unwound it, or you rotate it, then there will be a conformational change throughout the length or throughout the structure. Similarly, this 15-degree rotation due to breaking of salt bridges, this 15-degree rotation of one alpha beta subunit about the axis is going to trigger a conformational change in the rest of the hemoglobin molecule as well. Okay. These are the changes which will increase the affinity of the unoxygenated heme to the rest of the oxygen molecules. Why? Because now the salt bridges are already broken. Now the rest of the to break the rest of the salt bridges, you require less forces. Okay. So the subsequent, now you only need to storm. Suppose you're going to storm inside a fort. Okay, so the maximum effort is applied only to break the gate. After that, the rest of the crowd can storm in with ease. Similarly, the first salt bridge that was broken by the attachment of the first oxygen molecule, that was the most difficult because the structure was stable till then. After the salt bridge is broken, there is a conformational change by the twisting or the rotation of the molecule, and now it is extremely easy to break the rest of the salt bridges because it is now quite unstable. Therefore, this is what is known as cooperative binding. And this is an example of an allosteric behavior. Why? Allosteric means, allo means foreign or opposite. So what happens is, here after the attachment of oxygen at one site, there is ease or there is kind of a catalyzation for the attachment of the rest of the oxygens at different sites. Okay, not at the same site, at different sites. So this is kind of an allosteric behavior for hemoglobin. So allosteric effect we are going to read in the chapter of enzymes. That is, attachment at one site is going to facilitate attachment at another site. Attachment of a substrate at one site is going to facilitate attachment or reaction of another substrate at another site. Similarly, attachment of oxygen, of the first molecule of oxygen here on the hemoglobin molecule, is going to lead to ease or is going to lead to increased affinity for the attachment of the other oxygen molecules on that molecule. This is an allosteric behavior. It is an example of cooperative binding. It occurs because of breaking of salt bridges, because of the pull of the iron and the histidine F8, and it leads to the rotation by 15 degrees of 1 unit of alpha beta about the axis. Okay, extremely important. So you know how you understood how the structure of heme and the arrangement of histidine F8, histidine E7 is now coming into play, and how that is extremely important to read about the physiology. Okay, so this is how oxygenation was occurring. Now we understood how oxygenation is occurring in hemoglobin. Now, how does the delivery of oxygen occurs from the tissues to the lungs? Because that is also occurring by by hemoglobin only. So how is it occurring? See, for every molecule of oxygen consumed during respiration, one molecule of carbon dioxide is produced. So each carbon dioxide molecule has to be properly disposed of to prevent its toxicity building inside the body. So there are two contributors to dispose of this carbon dioxide. One, that is the major contributor, is the carbonic anhydrase enzyme. This enzyme catalyzes the conversion of carbon dioxide to the water soluble acid carbonic acid. This is by the carbonic anhydrase enzyme. Okay, now this carbonic anhydrase enzyme is the weak acid. Now again, we'll be going back to the first session. Weak acids. Okay, now strong acid donates protons to weak acids. Now, if you keep this weak acid in the plasma, this is present in the, this is occurring in the plasma. The concentration, the pH of plasma is 7.4. Okay. Now, the pKa for this is 6.35. So, compared to plasma, this bicarbonic acid, the carbonic acid is what? Carbonic acid is more acidic. Even though it is a weak acid, carbonic acid is more acidic compared to plasma. So it is going to exist in an ionic form. Okay, it is going to exist in an ionic form in the plasma. Why? Because it is going to donate its proton. Because it is going to behave as a strong acid here. Understood? Because it is a weak acid, but compared to the acidity of the plasma, it is a weak acid. Understood? So this carbonic anhydrase enzyme, it catalyzes the hydration of carbon dioxide and water to the water soluble acid carbonic acid, which is a weak acid, but compared to plasma, it is stronger. The pKa value is lesser, so it is a stronger acid, and it is going to exist in an ionized form like this. Okay. So the first contributor to dispose of carbon dioxide was the carbonic anhydrase enzyme. The second contributor is the ease of transition of hemoglobin between the T and R states. Okay, so what are the T and R states? The T state is the taut state. T state is the taut state or the deoxygenated state, which does not have the affinity for oxygen. The R state is the relaxed state, which has the affinity for oxygen. How are you going to remember it? If you're relaxed, and the people will be attracted to you. They will have affinity for you. If you're taut, you're passing taunts, then people won't have affinity for you. Okay, so they're not going to attracted to you. If you're very taut, if you're passing taunts, then people will not be attracted to you. So the taut state has less affinity, does not have affinity for oxygen, whereas the relaxed state, if you're relaxed and calm and composed, then people will have affinity for you. Then it has high affinity for oxygen. So what is the state that we are talking about here? You see, the salt bridges that were broken. Okay, the broken salt bridges state, that is the taut state. And the state which had the salt bridges, here the salt bridges are present. Oxygen is going to come and get attached to it. Here the salt bridges are broken. Salt bridges are broken. That is the state where the salt bridges are broken. The alpha and beta subunits have already twisted about the axis, and this is the taut state that is formed. And the relaxed state was where the salt bridges were already there. So they can transition between each other depending upon the attachment of oxygen. If oxygen is attached to the relaxed state, it triggers the formation of the taut state. And when the oxygen is released from the taut state, it triggers the formation of salt bridges and the reformation of relaxed state. So T and R forms can interconvert. Okay. Now, this carbonic anhydrase enzyme produces the bicarbonic acid, which is a weak acid and which exists in a ionic form, the proton and bicarbonate ion. We know this. Okay. So we're going to read further. Now, when the hemoglobin transitions between R and T state, then conformational changes will take place in each beta subunit, leading to formation of salt bridges between the side chains of aspartate 94 and histidine 146. Okay, so T state has broken salt bridges and R state has salt bridges. Okay, so what happens is when the hemoglobin will transition from R to the T state, then what will happen is the salt bridges need to be formed again. Okay, the salt bridges will need to be formed again. Once the oxygen gets attached to R state, then there is conformational change and salt bridges are broken. So once the oxygen is released, then the salt bridges have to be formed again. Now, how are they formed again? The beta subunit is going to form salt bridges with the side chains of aspartate 94 and histidine 146. Formation of each salt bridge will require one proton from the surrounding environment. Okay, so each beta subunit is going to form one salt bridge. There are how many beta subunits? There will be two beta subunits. So for each hemoglobin molecule, you will require two protons. So one beta subunit requires one protons to form one salt bridge. Now, one hemoglobin molecule has two beta subunits. So, for two beta subunits, you will require two protons to form two salt bridges per hemoglobin molecule. Understood? Now, the R state hemoglobin releases oxygen to tissues and changes to the T state. Of course, because once the R state has released oxygen, because the R state had affinity for oxygen. Okay, now when the R state has already released oxygen to the tissues, then it is going to convert to the form that does not have affinity for oxygen, and that is the T state. Now, once oxygen has been released, oxygen, as you know, is acidic. Therefore, the surrounding media will be acidified. Okay, the surrounding media is acidified because of oxygen, but at the same time, because it is converting into the T state, it is acquiring protons from the surrounding media. So if you're acquiring protons from the surrounding media, you are reducing its acidity. Therefore, the conversion of R state to T state gives off oxygen, but at the same time buffers the increase in acidity by taking in or absorbing protons. Understood? So therefore, this is how homeostasis is achieved. Okay. Now, the protons are absorbed. Now, what happens is when the protons are absorbed, then this part of the equilibrium is increased. See, the right hand of the equilibrium is increased. Therefore, the equilibrium will shift towards bicarbonate. Equilibrium is shifting here. And this bicarbonate is then going to release more of carbon dioxide. Understood? Therefore, this is how a lot of carbon dioxide is going to get collected from the tissues. How? Because at the tissue level, R state is going to convert to T state. For that conversion, you will require two protons. The two protons that are absorbed are going to shift the equilibrium towards bicarbonate side, and that is going to further the reaction and increase the conversion of carbon dioxide to bicarbonate. Okay, so this is all this is what is the Bohr effect. Okay, the proton release from R state hemoglobin enhances carbon dioxide released in the lungs. This also we know. Okay, the R state that had absorbed proton to form the T state is going to release the proton at the lung, at the level of the tissues, and it is going to enhance the release of carbon dioxide. How is this so? Because upon reaching the lungs, there is a dramatic increase in the partial pressure of oxygen. Okay, there is the partial pressure of oxygen at the level of tissues was less. Therefore, at the level of tissues, the R state, which had a high affinity for oxygen, is going to convert to T state. It is going to absorb the proton, and by absorbing proton, the equilibrium is going to shift towards bicarbonate. Therefore, a lot of carbon dioxide is going to get picked up from the tissue level. Now, at the level of lungs, there is an increased pressure of oxygen. Now, all the oxygen will come and bind to the deoxyhemoglobin. Now, from the T state to the R state, the change will take place. Okay. Now, T state to the R state, now there will be release of protons because the salt bridges that were formed between these aspartate 94 and histidine 146, these salt bridges are going to break. Now, what will happen is these protons that are released, they will combine with bicarbonate and they will increase the concentration of carbonic acid. It increases the concentration of carbonic acid. The equilibrium is going to now shift towards the left. And now what will happen is the carbon dioxide is going to get released. It is going to get increased in concentration and then it is going to get exhaled. Understood? So the equilibrium earlier at the level of tissues was going to get shifted towards bicarbonate, but the equilibrium here at the level of lungs is going to get shifted towards carbon dioxide and it is going to get exhaled. So this equilibrium that is existing between carbon dioxide, bicarbonate and carbon dioxide, carbonic acid, bicarbonate ion, and the R and T states transition, this whole proton mediated coupling is known as Bohr effect. Understood? So in short, at the level of tissues, R state converts to T state, oxygen is released, proton is absorbed. Why is proton absorbed? To form the salt bridges for conversion from R to T form. Protons are absorbed. Now this absorption of proton will shift the equilibrium towards the right and a lot of carbon dioxide is going to get absorbed and it is going to be taken to the lungs. Now at the level of lungs, the partial pressure of oxygen is very high. Therefore, T forms will get converted to R forms because of oxygenation. The salt bridges are going to be broken. Protons are going to be released. When protons are going to be released, then what will happen is the equilibrium is going to shift towards the left. And what will happen is the carbon dioxide is going to get exhaled. Okay, understood? So this is what the Bohr effect is. Now, this is 75% of carbon, 85% of carbon dioxide is transported in this manner, but 15% of carbon dioxide is transported attached to the amino terminal of nitrogen of polypeptide chains of hemoglobin as well. So carbon dioxide also is attached to hemoglobin as carb amino hemoglobin, but only 15% of it is transported in this manner. The rest is transported by how we just read. Okay. Now, the formation of this carb amino hemoglobin changes the charge on the amino group from positive to negative. Okay, because how carbon dioxide is attached to the amino terminal, then the positive charge on amino will change to negative. Now, this is going to favor the formation of salt bridges on the T state. Okay, now formation of salt bridges, formation of T state occurring at the tissue level. Therefore, this is what is going to enhance the Bohr effect. Formation of carb amino hemoglobin at the tissue level is going to enhance the Bohr effect or enhance the uptake of carbon dioxide at the tissue level. Tissue level, T state, proton absorbed, carbon dioxide taken. Lungs level, high PO2, R state, oxygenated, salt bridges broken, proton is released, carbon dioxide is exhaled. So this is in short the Bohr effect. Understood? Now what is the role of 2,3-BPG? Okay, now if you have seen my video on glycolysis made easy, another video available on this channel, I have mentioned the intermediates of glycolysis. One of them is 1,3-biphosphoglycerate, bisphosphoglycerate. 1,3-bisphosphoglycerate is a glycolytic intermediate. It gets converted to 2,3-BPG by 2,3-BPG synthase, and this has a very important role in hemoglobin physiology as well. What happens is the transition from R to T state is through the formation of salt bridges, and during that time, during the transition form, a central cavity is opened in between the 4 subunits. So when they are twisting about each other, when they are twisting by 15 degrees about each other, the salt bridges are getting formed from the R to the T state. Then what happens is there is a central cavity that is opened, and 2,3-BPG molecule that is present, it suddenly comes and binds to the cavity. Okay, it comes and binds to the cavity. Binding of 2,3-BPG favors the shift from R to T state and thus release of oxygen. Why? Because T state has low affinity for oxygen. Therefore, if 2,3-BPG is present in the environment, then what will be favored? Release of oxygen will be favored. Or T form or TOT form will be favored. TOT form is TOT or taunts. You don't have affinity for people who taunt. So TOT form has low affinity for oxygen. Therefore, 2,3-BPG will favor release of oxygen. How? It will come and bind to the central cavity of the interface of the 4 subunits. And how does it form? It binds by salt bridges. Okay, what are these salt bridges? They are between 3 amino acids, lys, hil, and val. Lys, lysine, histidine, and valine. How do you remember? Lys, his, walls. Okay, so this 2,3-BPG is going to take the walls of the 4 subunits on lys. 2,3-BPG is coming here and forming salt bridges with lys, his, and val. So lys, his, walls. Okay, this is the mnemonic. 2,3-BPG is going to lys, his, walls and form salt bridges in the central cavity of the 4 subunits. Okay. Now, what happens is when carbon dioxide is present in excess, it is going to cause acidification of blood. Therefore, during that time, formation of 2,3-BPG is triggered. What 2,3-BPG does is it reinforces the shifting of equilibrium in the favor of T state and increases oxygen delivery to tissues. Whenever there will be high carbon dioxide in the tissues, there will be formation of 2,3-BPG. 2,3-BPG is going to convert R state to T state. How? Because it is going to go and attach itself in the middle by these salt bridges to lysine, histidine, and valine. Okay, and that T form is going to get stable by this. Okay, and there will be reduced affinity for oxygen, and all the oxygen that was loaded on the R form is then going to get released. Okay. Now, fetal hemoglobin we studied had more affinity for oxygen compared to hemoglobin A, adult hemoglobin, right? The partial pressure of oxygen at which it was 50% saturated was 20 compared to the partial pressure of oxygen at which hemoglobin A was saturated, that was 26. So why is it so? Because fetal hemoglobin does not contain histidine 21 here. It contains serine, and serine cannot form salt bridges. Therefore, the T state of fetal hemoglobin is lesser stable. If it is lesser stable, then the affinity, because the T state has low affinity, so T state is lesser stable. That means R state cannot easily convert to the T state. T state will again go back to the R state, and the R state has high affinity for oxygen. Therefore, hemoglobin F has high affinity for oxygen. Because its T state is not easily stable, it again goes back to the R state, which has high affinity. And why is T state not stable? Because HbF contains serine instead of histidine 21. Lees his walls में his नहीं है, so the salt bridges cannot be easily formed. Okay, so everything is interconnected. Taut state, relaxed state, protons, carbon dioxide, oxygen, 2,3-BPG, everything is getting interconnected. Okay, now the effect of altitude. At high altitudes, a lot of physiologic changes are occurring, where what happens is at high altitudes, the number of RBCs is increased. In each RBC, the concentration of hemoglobin is increased, and the synthesis of 2,3-BPG also increases. Why does it increase? Because of hypoxia. Concentration of oxygen is less, concentration of carbon dioxide is more compared to oxygen. Therefore, the synthesis of 2,3-BPG increases, the number of RBCs increases, and the concentration of hemoglobin in each RBC increases. So this is all to cater the low concentration of oxygen at high altitudes. Okay. So what is favored at high altitude? Increased synthesis of 2,3-BPG. That means T form will be favored at high altitudes. Okay, so in a nutshell, if you have to remember, T form increases oxygen delivery to the tissues. Why? Because it has low affinity for oxygen. R form increases oxygen pickup at the lungs. Okay, because it has more affinity for oxygen. So this is in short. Next, the oxyhemoglobin dissociation curves and the oxymyoglobin dissociation curves. These are also extremely important. Okay, now if you see for myoglobin, the molecule of myoglobin is not dynamic compared to the molecule of hemoglobin. And one very important reason for that is hemoglobin is a tetramer. Okay, whereas myoglobin is a monomer. Now, for myoglobin, if you draw the oxymyoglobin curve, this is the percentage saturation of myoglobin, and this is the partial pressure of oxygen. Okay, now this is, suppose the partial pressure is 0 and percentage saturation here is 100, partial pressure here is 100. Here it is around 5, here it is around 20, here it is around 40. Okay, now myoglobin is easily, it gets saturated with oxygen, it keeps on binding to oxygen, it does not dissociate oxygen even at low concentrations of oxygen, that is even at 40 or 20. This is very low concentration of oxygen in the muscles and the tissues. So it is getting saturated with oxygen at, suppose, the level of lungs of the capillary bed at 100 millimeter of mercury pressure of oxygen, it is getting saturated. Now even if it is present at even if oxygen is at a lower concentration, it is not going to give off oxygen till the time that very low partial pressure of oxygen is encountered, that is during strenuous exercise. If the partial pressure is reduced to around 5, it is then that the oxygen will dissociate from the myoglobin molecule. So this is the curve. Okay, if the partial pressure is coming down to around 5, then only the percentage saturation of myoglobin is decreasing. Otherwise, it is the same, it is stable. So this type of a curve is a hyperbolic curve for myoglobin. Therefore, it is an excellent storage form of oxygen. It will store oxygen, right? And where is the storage occurring in our body? Mostly in the muscles. So what happens is, during normal exercise, myoglobin is not going to release oxygen. Okay, till the time when the muscles will get starved of oxygen. There is a lot of strenuous exercise and they're not getting enough oxygen. Then myoglobin will come into force and it is going to release its oxygen, and then it will permit the mitochondrial synthesis of ATP in the muscles. But this is very late when there is a lot of hunger for oxygen going on. Whereas hemoglobin is a dynamic molecule. What happens is, at low partial pressures, it will get saturated with oxygen at the lung capillary bed, okay, at around 100 mm of mercury of pressure of oxygen. Then when it encounters low partial pressure of oxygen, it is going to get converted to deoxygenated state or the taut state, okay. And once it reaches the tissue level, it is going to be converted into the taut state. So this is the how the sigmoidal curve of hemoglobin comes into force. Sigmoidal curve, okay. So this is at the level of lungs and this is at the level of tissues. Understood? So this is the sigmoidal curve of hemoglobin. It increases as you go to the lungs, but it will it will start dissociating as the partial pressure of oxygen is reducing. We saw how the interconversion between R and T states, the dynamic movement of the proton, the dynamic movement of involvement of the carbonic anhydrase mediated conversion of carbon dioxide to the weak acid. So all those things are involved in the hemoglobin induced delivery of oxygen at the tissues and pickup at the level of lung capillary bed. Okay, so this is the sigmoidal curve of hemoglobin and this is the hyperbolic curve of myoglobin. So this was all regarding hemoglobin and myoglobin. Now let us quickly jot down points of similarities and differences between hemoglobin and myoglobin on the first slide. Okay. Now the points of similarities. What are the similarities between myoglobin and hemoglobin? Both contain a heme ring. Okay, with a both are metalloproteins, right? Metalloproteins both have a ferrous core with a cyclic tetrapyrrole. Okay, so that cyclic tetrapyrrole is called porphyrin. Okay, cyclic tetrapyrrole is porphyrin. Porphyrin, when is attached to ferrous, that is the ferrous iron comes and attaches to porphyrin, it forms heme. Understood? So both have heme. Okay, both attached to oxygen. Okay, both attached to oxygen. In myoglobin and hemoglobin, the beta chain of hemoglobin and myoglobin both have beta hemoglobin and myoglobin both have 8 alpha helices. Right? Both have 8 alpha helices. This is important. Now, the points of differences. Myoglobin is mostly a storage form of oxygen. It is going to store oxygen. Hemoglobin is for oxygen transport and oxygen delivery. Okay, because of their nature. Next, myoglobin is a monomer. Hemoglobin is a tetramer. Okay, understood? Now, alpha chain of hemoglobin contains 7 alpha helices. Here, 8 alpha helices are there. Now, the oxyhemoglobin dissociation curve of myoglobin is hyperbolic. Sorry, oxymyoglobin dissociation curve. Whereas oxyhemoglobin dissociation curve is sigmoidal. I hope I think I'm covering all of the points. If I'm missing any point, then you can let me know in the comment section. So I hope all these points are making sense, and I hope um, this chapter has been made extremely easy to you. Please, the important points that I told were the structure of heme that we discussed, we drew. The structure of heme is extremely, extremely important. Then the physiology, that is also extremely important. How hemoglobin, how oxygen binds to hemoglobin, how carbon monoxide is not allowed to bind through steric hindrance, how hemoglobin is different forms of hemoglobin have different affinities, how the Bohr effect comes into play, and how the T and the R forms interconvert into each other. The basis of this chapter is this: how the T and R forms interconvert, how salt bridges are formed, how salt bridges are broken, how 2,3-BPG forms salt bridges inside by leasing his wall, that is, his lysine, histidine, valine. His or histidine is not present in HbF. Serine is present, therefore T form is not favored. R form, that is high affinity for oxygen, is favored. Therefore, histidine, fetal hemoglobin has higher affinity for oxygen. Okay, so few mnemonics you should remember. R form, relaxed individuals, people will have high affinity for them. Taut individuals or people who taunt each other, no one will have affinity for them. Therefore, taut form, low affinity for oxygen. Relaxed form, high affinity for oxygen. Okay, this is the basis. This you should remember. Bohr effect, very, very important. Bohr effect is extremely, extremely important. Okay, how proton is required for the formation of salt bridges. Salt bridges are formed at the level of the tissues where R converts to T state. R converts to T state, salt bridges are formed, protons are absorbed. Therefore, when protons will be absorbed, then what will happen is more of this is going to take place. Okay, in this reaction, if this is getting absorbed, this is getting reduced, then more of this will need to happen for the equilibrium to be stable. So therefore, more of carbon dioxide will be taken up. Okay, so if proton is absorbed, if H plus is getting reduced, what will happen? To maintain this equilibrium, this reaction will proceed towards H plus, so that more H plus gets produced. H plus is getting taken up, so this reaction will proceed towards H plus, so that more H plus is getting produced and more of carbon dioxide will be taken up, and from the tissues, maximum carbon dioxide will get be taken up in the blood. Okay, now at the level of lungs, what happens is the R state will, the T state will change to R state. The salt bridges will be broken. Protons will be released. Carbon dioxide will be expelled out. How? Protons will be released, then this will increase. H plus will increase. The reaction will proceed towards this side to reduce it. Okay, so that the equilibrium is maintained. Now more of carbon dioxide will be produced, carbon dioxide will then be exhaled. So this is in the summary of Bohr effect, which forms the basis of carbon dioxide transport. Okay, role of 2,3-BPG we already know. Role of altitude, that also we know. Okay, the oxyhemoglobin dissociation curves and the oxymyoglobin dissociation curves, the shape of the curves, and what is the clinical application. This is also very, very important. So I hope you understood today's session, and I hope that you go back and you draw the assignment for you guys is to draw the structure of heme, to draw the oxyhemoglobin and oxymyoglobin dissociation curves, to tabulate the similarities and differences between myoglobin and hemoglobin, and to jot down points of oxygen transport, carbon dioxide transport, Bohr effect using hemoglobin. Okay, so all these things you should do, you should write down in your notebook, and that will be enough practice for you guys from this chapter. So going forward, after this, we are going to start the chapter on enzymes, which forms a huge chunk in biochemistry. So if you are thorough with enzymes, if you're clear with enzymes, a lot of your mental load is going to be shed off. So a few days from now, we are going to start with enzymes. So keep on revising whatever sessions we are going through. So because we are going to derive a lot from the earlier sessions, okay, just like this. We took a lot from the last session in this chapter as well. Okay, so I hope you like this session, and we are going to meet soon in another high yielding session. Okay, bye bye, take care.